So we've just finished covering sections 4.3 and 4.4. So we're gonna be reviewing or summarizing the key concepts that we learned and going over some additional problems. First thing is that section 4.3 is about the mean value theorem, which implies, among other things, that if f prime of a function is positive on an interval, then the function is increasing. There, and if f prime is less than 0, on the other hand, then f is decreasing in AB. So 4.3 is all information about the first derivative and what you can say about the function based on the knowledge of the sign of f prime. Some applications, besides besides characterizing critical points, include, say, saying whether a polynomial or not has a certain number of roots, which asks you to combine the intermediate value theorem and the mean value theorem. We went over an example like that a couple of videos ago. Now, for the characterization of critical points, we use what's called the first derivative test. Critical points. So we have what's called the first derivative test. And what does it say? If we have a critical point, C is a critical point, then if f prime changes from plus to minus, then that C corresponds to a local max. If, on the other hand, f prime changes, if instead changes from minus to plus, then C corresponds to a local min. And that's the first derivative test. It allows you to look at a critical point in the sign of f prime at both sides of the critical point, and it tells you whether that point corresponds to local max, local min, or neither. Okay, that's the information we can draw from the first derivative. Now, for section 4.4, we get information from the second derivative. So this is the shape of f based on the sine of f double prime. Remember, of function is concave up if f prime is increasing. Sorry about that. It's concave up if the function is increasing, if f prime is increasing, and is concave down. It's concave down if f prime is decreasing. So just like before, when we could draw information about f from f prime, we can draw information about f prime and the growth of f prime from f double prime, because the derivative of f prime is f double prime. So we have a criterion that says that if f double prime is positive inside an interval, then that means that f prime is increasing. So this implies that f is concave up inside a comma b. If f double prime is negative, on the other hand, then f is concave down on the interval a comma b. And this also has the second derivative test, which says that if we are at a critical point, if c is a critical point, f is nice enough, then if f double prime at c is greater than 0, this implies c corresponds to a local min. If f double prime at c is negative instead, then c corresponds to a local max. F double prime positive means that the graph near that point where the derivative vanishes looks like that. F double prime and c being negative, it means that it's bending like this. So it's clear from these pictures here that when the second derivative is greater than 0, then c corresponds to local min, and when the second derivative is negative, then c corresponds to local max. Okay, so without having to look specifically at f prime right before c, right after. However, if f double prime at c is equal to 0, the test doesn't tell us anything. The test is inconclusive. So we cannot deduce anything because you have actually examples where the functions can be, I mean the critical point can be either a local max, local min, or neither. So look at f of x is equal to x cubed, which is something we talked about before. Then f prime of x is 3x squared. So this implies that 0 is is a critical point. And now what happens at 0 in terms of the second derivative? F double prime of x is 6x, so f double prime at 0 is equal to 0. Is x local min or local max? Well, it's actually neither. You see what happens here? So this is x cubed. So the function is actually increasing. Always, even at 0. So this critical point over here is not a local max. Look at what happens for positive x. There are values nearby that are greater than 0. And it's not a local min. If you look on for negative values of x, you see that the values are smaller than 0, so it's not a local min either. F of x. Oh, so let me, before jumping to the next example. So you see here the f double prime at the point is equal to 0, and in this example the point is neither a local max nor a local min. So there cannot be a rule that tells us that this thing has to be either a local max or local min, because we have an example where it is neither. Right, and we also have examples like f x is equal to x to the 4th, where f prime, this is another example, this is another example, f prime of x is equal to 4x cubed, f double prime of x is equal to 12x squared. Then we see that 0 is again a critical point. If you plug 0 in here, you get 0, so that's a point where the derivative vanishes, so it's a critical point. And f double prime at 0 is still equal to 0, because 12x squared at 0 is 0. And the test is inconclusive, so we say, oh, is it always the case that it is neither a local max nor a local min? Well, this example here proves that that's not the case either. So because here 0, well, this corresponds to a local min. If you look at the function x to the 4th, it looks sort of like a steep parabola. You see that for positive values, of course, the function x to the 4th is positive, but also for negative values, because this is x squared, right? So it looks more or less like this, and 0 corresponds to it's a local min. If instead you would consider the function minus x to the 4th, then 0 would be a local max. And so you can have every possible option when the second derivative is equal to 0. So you cannot really conclude anything just from that, which is the point I was trying to make. So be very careful when you apply the second derivative test. Now, in the next The next few examples, we'll try to complement the analysis we made before I mean, the examples we covered when we covered each section are the most relevant, and they're the ones that you're most likely to see in an evaluation. But there are some others that are perhaps less common, but maybe, I mean, who knows? You may be asked to solve something related to those. I mean, I don't see it, especially now that we've switched to an online format. I think I would be very surprised if you were asked to do anything more complicated than what we went over with these examples involving polynomials. But I mean, I'm just gonna try to give you a complete picture. So I'm gonna be going over a few examples in the in the next few videos.